Hello everyone. Today we will look at learning algorithms for probabilistic graphical models. Last class we looked at machine learning fundamentals as well as some machine learning principles. Today what we'll do is we'll apply these principles as well as fundamentals to derive new learning algorithms. Altogether, in this course, we will cover 16 classes of learning algorithms, and I will describe what they are next. In this course, we will divide the learning algorithms along 4 dimensions. This is dimension number 1, number 2, number 3, and number 4. The first dimension is the dataset types, and it takes 2 values, fully observed and partially observed. Recall that each dataset can be represented by a matrix in which the rows represent the examples and the columns represent the variables. We say that a dataset is fully observed if all variables in the graphical models are observed in each example of the dataset. So for example, if you have a dataset which is, let's say, defined over 4 variables and has 5 training instances or 5 examples, and each example is such that each variable is known. So let's say the variables take binary values and all of the examples are complete. Then we call such datasets as fully observed datasets. Otherwise, we say that the dataset is partially observed. The second dimension describes what is being learned in the graphical models. It takes 2 values, parameter learning and structure learning. In parameter learning, we assume that the structure of the graphical model is given to us. Namely, in Bayesian networks, we are given a directed acyclic graph, and in Markov networks, we are given the scopes of all potentials. Then the parameter learning task in Bayesian networks is to learn the probabilities in each conditional probability table from data. Similarly, the parameter learning task in Markov networks is to learn the potential values from data given the scope of each potential. Since in structure learning, we have to learn both the structure as well as the parameters of the graphical model from data. Structure learning includes parameter learning as a subproblem, and therefore is a much harder problem as compared to parameter learning. The third dimension is the learning approach used. Okay? So in statistics, there are 2 popular learning approaches. One is called the maximum likelihood estimation approach, and the second approach is called the Bayesian approach. The maximum likelihood estimation approach is based on the maximum likelihood estimation principle, as the name suggests, and what it relies on is the data to do all the talking. What I mean is that the MLE principle, or the maximum likelihood estimation principle, relies only on the data to perform the learning task, while the Bayesian approach combines data with prior knowledge to learn a graphical model. The fourth dimension is the type of graphical model used. Namely, whether we are learning a directed model or a Bayesian network, or we are learning an undirected model or a Markov network. Thus, if you see, we have 4 dimensions, and each dimension can take 2 values each, and therefore the number of combinations is 2 to the power of 4, which is equal to 16. That is why I said that we will learn 16 classes of learning algorithms in this course. So let us begin with the easiest class of learning algorithms. We will develop algorithms that learn Bayesian networks using the maximum likelihood estimation approach, and we'll only learn the parameters of the Bayesian network. Namely, we'll assume that the structure of the graphical model, or the Bayesian network in this case, is given to us. Moreover, we will assume that the data is fully observed. Before we discuss the learning algorithms, uh, let me discuss the maximum likelihood estimation principle, which is a general principle for learning probabilistic models from data. The main idea in the principle is that given candidate probabilistic models, you should select, and let's say the candidate probabilistic models are given by M1 to MT, you should select a candidate MI from this set such that the data is most probable with respect to MI. Okay? So this is an intuitive approach in the following sense, that if you have a bunch of candidates, which is the candidate that you're going to pick? The candidate that works the best on the data that you have, which is your input. Okay? So that's why this approach is widely used in practice, because it's very intuitive and very straightforward. Mathematically, or more theoretically, we can express the maximum likelihood estimation principle as the following. Let's say you are given a data set D with examples x1 to xm and a probabilistic model, let's call it PR, which is defined using a set of parameters theta. In MLE, what you're trying to do is you want to find a setting of the parameters in theta such that the likelihood of generating the data, okay, which is given by this quantity, which is the product of the probability of generating each data point according to the given theta, is maximized. Okay? Mathematically, what you want to do is you want to find a setting of the parameters, which is, let's say, called theta star, such that this likelihood quantity is maximized. Okay? So what is the likelihood? Likelihood is nothing but the product of the probability of generating each point according to your current model. Okay? So let me give you an example. Let's say you have a model M1 and let's say you have a model M2. So let's say these are the only two candidate models that you are considering, and let's say M1 is such that you have a set of parameters which are, let's say, probabilities which look like 0.2, 0.3 and 0.7, and M2, let's say, has probabilities which look like 0.6, 0.4 and 0.8. Okay, so these probabilities don't sum to a 1 because I'm using so-called minimal parameters. So maybe you can imagine that the other parameter associated with 0.2 is 0.8, the second parameter associated with 0.3, which I'm not representing because the other parameter could be computed as 1 minus of 0.3 is 0.7 and so on. So let's say you're given these two models, M1 and M2, with this parameter set theta 1 and theta 2. Which of these two models will you use if you are given a data set D? And the idea is that what you'll do is you'll go through each example in the data set, and let's say the data set has two examples, x1 and x2. Okay? What you're going to do is you're going to compute the probability of x1 according to the parameter setting theta 1. So this is nothing but the model M1. Okay? And you will compute the probability of x2 again according to the parameter set, I should say, theta 1. Okay? So when you take the product of these two probabilities, what will you get? You'll get the likelihood of the data according to the model M1. Okay. Similarly, what you'll do is you will compute the likelihood of the model according to model M2, which is P of x1 with respect to theta 2 times P2 of x2 with respect to theta 2. Okay, so this is the likelihood for model 1 is equal to that, and this one is the likelihood for model 2. Okay, so which model will you choose now? You will choose the model that has the highest likelihood. So if it turns out that L1 is greater than L2, then you will choose the model M1 according to the maximum likelihood principle. If L2 is greater than L1, then you will choose the model M2. Okay, so that's the maximum likelihood estimation principle. The idea is that you just compute the likelihood, and the model that has the highest likelihood among the candidates is the model that will output to the user. Let us use another example, right? And the example of a biased coin to illustrate the ideas in maximum likelihood estimation. So let's say you're given a biased coin, and we model that biased coin using a variable x, and let's say x has two outcomes. H is equal to head and T is equal to tail. Okay? So let's say now you're given a data set which is nothing but different tosses of the coin. An example data set will look something like this. You toss the coin 100 times and it landed heads 60 times and landed as tails 40 times, right? So that's your data set. What we will do is we will assume a probabilistic model over the variable x, and since there is only one variable, we'll assume that the probabilistic model is parameterized by a parameter theta. So probability of x equals h, which is x equals heads, is equal to theta, and probability of x equals tails will be equal to 1 minus of theta. Okay, so we will say that this particular probabilistic model is parameterized by this parameter theta. So there is just one parameter in the set. So candidate models are those models that have different values of theta. Okay, so that's my set of candidates. Is the set of candidates finite or infinite? I'll give you 1 minute to think about it. The 1 minute is over since this is an online class and this is a running joke. The idea is that theta will have infinite number of values because theta is a real number. Okay, so among these infinite set of candidate models, you are going to choose the one model, okay, or the one value of theta such that the likelihood of the data is maximized. Okay, you actually already know how to answer this question. Suppose if I give you a data set that has 60 heads and 40 tails out of 100, then what is the maximum likelihood estimate theta star? And the answer is, I gave you some time to think about it, the answer is nothing but theta star is equal to 60 divided by 100. Okay? Because this is intuitively the best estimate of probability. Now let us see how we can compute the maximum likelihood estimate for our biased coin example given a data set using a plot of the likelihood function. Okay, so if you remember, we are given a parameter theta, which is the probability that the coin lands heads, and 1 minus theta, which is the probability that the parameter, or I should say the coin lands tails. Our evaluation metric here, which is we are going to use the maximum likelihood principle, says that we should select a model such that the probability of generating the data is maximized, right? Or the likelihood of generating the data is maximized. In a way, it tells us how well we can predict the data. So let's say you're given an example data set in which you have 3 heads and two tails. Okay. What is the likelihood of the data? The likelihood of the data according to the parameter theta is theta times theta times theta, because we have three heads, times 1 minus theta times 1 minus theta. Okay. So what I can do is I can rewrite this function as nothing but theta cube times 1 minus theta square. Okay. This is nothing but a function over theta. And if I want to maximize this function, one easy way that I can use to maximize this function is just go to Google and put the command plot f of theta is equal to theta cube times 1 minus theta square, right? And then what you'll do, and I should say what you'll get is a curve that looks like that. Okay. From this, you can figure out that the maximum value appears at something like 0.6, or I should say maximum value appears as at 0.6, right? Okay. So on the y-axis, I have the likelihood for each data point, and on the x-axis, I'm varying the value of theta. Okay. So for example, when theta is equal to 0.2, how did I compute this quantity? The way I computed this quantity was 0.2 cube times 1 minus 0.2 squared. Okay. Similarly, when theta was 0.4, how did I compute this quantity over here, right? The likelihood, that is going to be equal to 0.4 cube times 1 minus 0.4 squared. Okay. So this is how you can solve the MLE problem, right? Or compute the maximum likelihood estimate for any parameter, right? Just plot the likelihood function and figure out what the maxima is. This is easy to do in the one-dimensional setting. Okay. Unfortunately, this approach is not generalizable to higher dimensions. So instead of having just one theta, let's say you have thousands of thetas. How do you plot that function and do visualization and figure out what the maximum likelihood estimate is? Okay. So what we need are mathematical tools, right? What I mean by mathematical tools is we need some equations so that we can convert those equations to programs and use software to compute maximum likelihood estimates in the general setting. And that is what we are going to discuss next. A more general method, as compared to using the so-called plotting method that we discussed on the previous slide, is to derive the maximum likelihood estimate analytically. Okay, so one approach for that is to differentiate the likelihood function with respect to theta and set the derivatives to 0 and then solve for theta. Why will this approach work? The reason this approach will work is that the derivative is 0 at so-called maximas, minimas, and saddle points of the functions. Okay, so to give you an example, let's say you have a parameter theta in one dimensions, and then so only one parameter theta, so that's why I'm saying that there is only one dimension. And let's say you're trying to compute the likelihood of theta with respect to a given data set D, and you plot it and you get, let's say, something like this. Okay, so when is the derivative 0? The derivative is nothing but the tangent line to the likelihood curve. Okay, so the derivative will be 0 when the tangent line is parallel to the x-axis. So at this point the tangent line is that, and it's parallel to the x-axis, and so it's 0. So this is nothing but the so-called maxima of the function. Okay, the derivative will be 0 again over there, and that is nothing but the so-called minima of a function. And it will also be 0 at these saddle points, which are neither maximas nor minimas, or plateaus. Okay? So, how will you use the derivative method to do this? So, you take the derivative of the likelihood function with respect to theta. Okay? You'll figure out that theta is 0 at multiple points. All you have to do is evaluate those points using the likelihood function and pick the point that has the highest value for the likelihood function. Because remember, we are trying to maximize the likelihood of the data. So it turns out that if you take the likelihood function that is given to us, which is nothing but theta cubed times 1 minus theta the whole square, if you take the derivative of this with respect to theta and solve for theta, you will realize that you will get theta star, which is equal to the number of heads divided by number of heads plus number of tails, right? So one way of saying this is, if I have 60 heads and 40 tails, then I'm going to do 60 divided by 60 plus 40, which is nothing but 0.6. Okay? How did I compute this value? Okay, so let's try to do this for our likelihood function, which is theta cubed times 1 minus theta squared. So one trick that we can use is that since log is a monotonic function, and since taking derivatives of logs is easier, instead of maximizing the likelihood, what we will do is we'll maximize the log likelihood of the data. Okay? The reason is that if we maximize the likelihood and we get a solution, and then let's say we maximize the log likelihood and we get a solution, since log is a monotonic function, the two answers will be the same. Okay? So no difference between those two answers. And the good news is that taking derivatives in the log space is easy. So let's consider the log likelihood of data with respect to theta. This is nothing but 3 times log of theta plus 2 times log of 1 minus theta. Okay? And now let me erase some of the drawings and let me try to take the derivative of the quantity that is given on the slide with respect to theta. Okay, so what is the derivative of this one with respect to theta? This is equal to 3 divided by theta, because the derivative of log theta is 1 divided by theta plus 2 times 1 minus theta into minus 1. Okay, so we equate this derivative to 0, and we know that this is nothing but 3 times 1 minus theta minus 2 times theta is equal to 0. So we have 3 minus 3 theta minus 2 theta is equal to 0. Okay, so this is equal to, this is the same as, I should say, 5 theta is equal to 3, and so theta is equal to 3 divided by 5, which is nothing but, in general, number of heads divided by the total number of examples. And the number of examples is nothing but number of heads plus number of tails. So you get that formula. Next, what we will do is we will extend the MLE principle. MLE is the maximum likelihood estimation principle, from the univariate case to the multivariate case, specifically to Bayesian networks. The parameters of the Bayesian networks are the probability values in the conditional probability tables. Remember that we are interested in parameter learning in Bayesian networks given the structure. In other words, we have the precise form of each CPT and the parameters that the CPT uses. Okay? And we are trying to learn those parameters from data. So what I will do is I will demonstrate the approach in the multivariate setting using a simple example which is defined over two variables. Okay, and then we will come up with a general formula for parameter learning in Bayesian networks. And I'm calling it a general formula because instead of being a really complicated algorithm, what we have is a closed form solution for parameter learning in Bayesian network under the assumption that the data is fully observed. Okay, so that's why this algorithm is beautiful and simple. But let us demonstrate it using this example. So let's say you are given a Bayesian network with two variables, x1 and x2, and there is an edge between x1 and x2. Okay, there's a directed edge between x1 and x2. Let's say the parameters of this model are given by theta. So we have a parameter theta 1, theta of 2 given 0, and theta of 2 given 1. And we are also given a data set D. Okay, so let me draw this Bayesian network and precisely specify the parameters. So x1 is associated, x1 has a CPT, which is P of x1, and that is associated with the parameter theta 1. So let us assume that x1 equals 0, or probability of x1 equals 0, I should say, is equal to theta 1, and probability of x1 equals 1 will be 1 minus theta 1. So for P of x2 given x1, we have two parameters. One parameter is theta of 2 given 0, which is nothing but P of, let's say, x2 equals 0 given x1 is equal to 0. And the second parameter is theta of 2 given 1, which is nothing but P of x2 equals 0 given that x1 is equal to 1. Okay, so this Bayesian network, simple Bayesian network over two variables, has three parameters associated with it. And let's say you are given a data set D. This is a fully observed case. So the data set D will consist of examples of the form x1 is assigned some value and x2 is assigned some value. Okay? So the task that you're interested in solving is find a setting for these parameters theta, which means that find a setting for theta 1, theta of 2 given 0, and theta of 2 given 1, such that the following likelihood function is maximized. Okay? So the likelihood of the data given a set of parameters theta is defined by the expression that is given on the slide. Right? So let me focus on that expression and erase some of the drawings that I've made. So the expression, if you see, has three terms which are enclosed in bracket. So the first term is saying that the probability of the data with respect to the parameter theta 1, okay, is theta 1 to the power of the number of examples that have x1 equals 0 times 1 minus theta 1 to the power of number of examples that have x1 equals 1. How did I come up with this expression? The same idea as before, right? So if you remember in the previous slide, we had 3 heads and 2 tails, and I can write the likelihood expression as, if you remember, theta cube into 1 minus theta square, right? So the general form is nothing but theta to the power of number of heads into 1 minus theta to the power of number of tails. Okay? So this is the same thing. What we have here is theta 1 to the power of number of data points that have x1 equals 0 into 1 minus theta 1 to the power of number of data points that have x1 equals 1. Let us look at the second term, right? So the second term is saying that I have theta of 2 given 0 to the power of number of data points that have x2 equals 0 and x1 equals 0 into 1 minus theta 2 given 0 number of data points to the power of, I should say, number of data points that have x2 equals 1 and x1 equals 0. Okay? So where did that come from? That came from the fact that only some examples, right? Or I should say only those examples which have x2 equals 0 and x1 equals 0 are relevant to the parameter theta 2 given 0. Similarly, only those examples that have x2 equals 1 and x1 equals 0 are relevant to the parameter 1 minus theta of 2 given 0. Okay? So, since this is a product, those terms will only be considered when the data set has this property. Okay? So, I'm just going to count over them. Similarly, I get the expression for theta of 2 given 1. If you look at the expression for likelihood, you will quickly realize that this likelihood expression is decomposable. What I mean is that each parameter is actually involved in just two terms. So for instance, theta 1 is involved in just two terms, this particular term as well as that term. Okay? Theta 2 given 0, which is another parameter, is also involved in two terms. And same thing with theta of 2 given 1. Okay? As we said in the previous slide, it is often a good idea to consider log likelihood of data rather than considering likelihood of data, okay? Because it's easy to differentiate the log likelihood rather than differentiating the original form of likelihood. So what I'm going to do is I'm going to take the log of this expression and write the expression for log likelihood. If you remember, if I'm trying to compute log of theta to the power of k, this is nothing but k times log of theta. Okay. Similarly, I know that log of x1, x2 is nothing but log of x1 plus x2. Or I should say log of x1 plus log of x2. So using these two rules, I'm going to rewrite the expression for likelihood as follows. Likelihood of the data with respect to the given parameters theta is equal to the number of data points that have x1 equals 0 times log of theta 1 plus the number of data points that have x1 equals 1 times log of 1 minus theta 1. Okay? And so on for the other expressions in the brackets. Okay? So this bracket becomes that expression and that bracket becomes that particular expression. Okay. So now the question is, likelihood is decomposable and because each parameter is involved in just two terms. So how do I use this fact? I can use this fact because I can take derivatives of the log likelihood of data and equate it to 0 in order to find the so-called maximas of the log likelihood function. Okay? And the beautiful thing about these derivatives is that each of these derivatives will only involve two terms. Okay, so when I take the derivative with respect to theta 1, I'm only considering these two terms because the derivative of the other terms with respect to theta 1 will be equal to 0 because they don't involve theta 1 at all. Okay, similarly, whenever I'm taking the derivative of theta of 2 given 0, I'm only considering the terms that are given here, right? And all other terms will disappear because the derivative will be equal to 0. Okay? So if I take derivatives and equate those derivatives to 0, I get three closed form expressions for my parameters. Okay, so let's look at those expressions. Theta 1 is equal to the number of data points that have x1 equals 0 divided by the number of data points that have x1 equals 0 plus the number of data points that have x1 equals 1. Okay, another way of saying this is nothing but number of data points that have x1 equals 0 divided by the total number of examples. And let's say there were m examples. Okay? Theta of 2 given 0 is equal to the number of examples that are related to theta of 2 given 0, which is the number of examples that have x2 equals 0 and x1 equals 0, divided by the number of examples that appear in the term for log of theta of 2 given 0 plus the term for log of 1 minus theta of 2 given 0. Okay, so we get these expressions Okay, another way of writing this is by saying that theta of 2 given 0 is nothing but the number of data points that have x2 equals 0 and x1 equals 0 divided by the number of data points that have x1 equals 0. Okay, so if you recall, theta of 2 given 0 is nothing but probability of x2 equals 0 given x1 equals 0. Okay, so if I give you data and I ask you to compute this probabilities and compute this probability, I should say, the first expression that comes to your mind is the following. This is nothing but the number of examples that have x2 equals 0, comma x1 equals 0 divided by the number of examples that have x1 equals 0. How did I come up with this expression? The numerator is an estimate of p of x2 equals 0, comma x1 equals 0, right? Or I should say it's directly proportional to that. And the denominator is directly proportional to x1 equals 0. Okay, so that's the maximum likelihood estimate. So in general, okay, so if you like, write down the general expression for log likelihood. And let's say you are given a data set D, the MLE solution for the parameters, which is this theta star, will always have the following closed form solution. Okay, and the closed form solution is saying that the MLE solution for the parameter xi given parents of xi, okay, is equal to the number of data points that have the value xi equals small xi, comma parents of xi equals small parents of xi. So this is an assignment to the corresponding value for parents of xi divided by the number of data points that have the corresponding assignment for parents of xi. Okay, again the numerator is proportional to the joint probability of xi comma parents of xi, and the denominator is proportional to the probability for the assignment to the parents of xi. Okay, so that's the maximum likelihood estimate. It's a very intuitive estimate. So often these counts that we compute from data over xi comma parents of xi, these counts are called sufficient statistic. Okay, sufficient statistic for this estimate. If you remember from your statistics class, any function of the data is called a statistic, and a sufficient statistic is defined as a statistic that contains all the information in the data set that is needed for a particular estimation task. Okay? In other words, what this means is that once you have access to the sufficient statistic for a data, you can actually throw away the data. Okay? So if you remember, for estimating the parameter theta in our bias coin case, all we cared about is the number of heads as well as the size of the data. Okay? We did not care about what each individual outcome was in the data set. Okay? So as long as you maintain the number of heads or you keep a count of the number of heads, I don't care about whether fifth example was a head or the eighth example was a head or the 10th example was a head. Right? All I need to know is the number of heads appearing in the data set. Okay? So number of heads in this case is a sufficient statistics, and that's the information that you need to maintain rather than the whole data set. Now let us derive the maximum likelihood estimates for an example Bayesian network as well as data set given on the slide. Okay? So the Bayesian network has three variables: health aware, smokes, and exercises. Let's represent the variable health aware by H, smokes by S, and exercises by E. Let us say that each variable can take two values, true and false. Okay? And let's say we have access to a data set which has 16 examples, 1 to 60, where the first example is health aware is true, smokes is false, and exercises is true. Okay? The second example is health aware is true, smokes is false, and exercises is true, and so on. So what we want to do is use our previous discussion and compute the most likely estimates for each of the parameters in this Bayesian network. So health aware is associated with a parameter, let's call it theta h. Smokes is associated with two parameters, one for smokes given h equals 0 and another for smokes given h equals 1. Okay, so let's call this parameter as theta of s given h equals 0 and the second parameter as theta of s given h equals 1. Okay, so what is theta of h equals, or I should say, what is theta of h? Theta of h is equal to the number of times h is equal to false divided by the number of times h is equal to false plus the number of times h is equal to true. Okay, so all I have to do is count the number of times h is equal to false, because we know that the denominator is 16. So let's count. So we have h equals false once, twice, thrice, and 4 times. Okay, so h is equal to false 4 times out of 16, so the probability is 1 over 4. What is theta of s given h equals 0? This is equal to the number of times I see s equals 0 and h equals 0 divided by the number of times I see h equals 0. Okay, so the number of times I see s equals 0 and h equals 0, let's count, or 0 here in this case is false. So I see false and false tuples once, I see it twice, thrice, and that's it. Okay, so this is going to be equal to 3, and we already know that the number of times h is equal to false is 4, so it's 3 over 4. Okay, similarly we can compute other parameters such as theta of s given h equals 1, as well as theta of e given h equals 0 and theta of e given h equals 1. Okay, so if you do the counting on this data set, you will realize that these are the maximum likelihood estimates for the different parameters. Okay, so h bar is nothing but h equals false, and h is nothing but h equals true. So we already computed this parameter, which was 1 over 4, and we computed this parameter, which was 3 divided by 4. Okay, and you can similarly compute other parameters using the data set given on the previous slide. So here are some final points that I want to make on MLE learning in Bayesian networks. The first is, what is the impact of data size? So we did not talk about data size at all. We just assumed that the data is given to us. But as you can imagine, if I give you 2 data sets and one data set is larger than the other, then you are always going to be more confident about the larger data set, or the estimates that are generated or computed from the larger data set than the smaller data set. Okay, so let me now try to have this discussion in a more concrete fashion. So the first point is that ML estimates, or the maximum likelihood estimates, will have different values depending on the size of the data set. Okay, so and this is where like the bias versus variance trade-off comes into the picture, in the sense that the bias of the model is already known. We cannot change the bias of the model because the structure of the model is already given to us. What we can change here is just the variance. And we know that the variance goes down, or the variance of the estimate will decrease as the size of the data set increases. Okay? So the only way in which we can use the bias versus variance trade-off is by increasing the size of the data set in this case. The third point I want to make is that estimating probabilities that are quite small is extremely hard because a large number of samples are required to reach a reliable estimate. And we already saw this when we covered sampling theory. We said that whenever the probability of evidence, for instance, is very, very small, then rejection sampling will often fail. Okay? So the same principle applies here. So if you're trying to estimate probabilities which, let's say, are something like, whether the true probability is something like 10 to the power minus 10, in general, okay, you will have to see at least 10 to the power 10 samples before you can estimate this probability reliably. Okay? Otherwise, in many cases, what will happen is the estimate for this probability based on the data will be equal to 0. Because in a way, you're performing rejection sampling or using the rejection sampling estimate to compute the maximum likelihood estimate. Some other properties that I want to highlight is that the likelihood function in our case was unimodal. Okay? And as a result, our ML estimate or the maximum likelihood estimate was unique. It's always the so-called maxima point, if you remember. There's only one maxima point, and that maxima point is unique. Okay? The x-axis was theta, and the y-axis was likelihood of theta. The second point is that ML estimates can be computed for this parameter learning problem when the structure of the Bayesian network is given and the data set is fully observed. This ML estimate can be computed in closed form. In general, ML estimates cannot be computed in closed form. Okay? You are going to use mainly iterative types of approach, such as gradient descent or expectation maximization, in order to compute ML estimates. But at least for this problem case, ML estimate can be computed in closed form, and that is why this particular problem type has low computational complexity or low estimation complexity. In fact, the computational complexity is linear in the number of variables, the number of parameters, as well as the number of examples. So that concludes our discussion about maximum likelihood estimation in presence of, if you remember, fully observed data. Okay? Then we were doing parameter estimation. We were doing this parameter estimation on Bayesian networks, and we were using the maximum likelihood estimation principle. Now let us look at the second case, or the second machine learning algorithm type that we are going to discuss, which is parameter learning in Bayesian networks using the MLE approach under the assumption that the data is only partially observed. Okay? Examples of partially observed data abound in the real world. For instance, most healthcare data sets will have some missing data or missing information in them. Often, in some data sets, some variables are always missing because they are hidden variables which are never observed. Okay, so these might be so-called estimation variables that you are interested in, but you will never observe them for real in the data set unless you have expert knowledge. Unfortunately, as we will see that by just changing the condition from fully observed data to partially observed data, the algorithms become quite complex. In that, closed form solutions are no longer possible, and we have to use iterative approaches such as gradient ascent and the expectation maximization algorithm to solve this problem. So the first question that we want to answer is, why is parameter learning so hard, or why is it so challenging in presence of partially observed data? And the reason is actually quite simple. If you remember the expression for the likelihood function in presence of fully observed data, the likelihood function was decomposable and it was unimodal. Unfortunately, the likelihood function in the context of partially observed data has this ugly summation term because you have to sum out all the missing variables in the graphical model in order to compute the likelihood. And as a result of this summation term, the likelihood function is no longer unimodal. It's actually multimodal. Okay? And because of this summation term, the likelihood function is also not decomposable. Okay? As a result, there are no closed form solutions for the likelihood function. So to give you an example of why the likelihood function is not decomposable and unimodal, let me use a Bayesian network. So let's say you have a Bayesian network, same Bayesian network as before, from x1 to x2. And if you recall, the parameters that we used were theta 1 that was associated with x1, theta of 2 given 0 that was associated with x2, and theta of 2 given 1 which was associated with x2 again. Remember, in the fully observed data case, we got nice closed form expressions for theta 1, theta of 2 given 0, as well as theta of 2 given 1. This is because the likelihood was unimodal as well as decomposable. In the partially observed data case, let us assume that x2 is the observed variable and x1 is always hidden. Okay, so I'm just going to shade x2. So the likelihood will now be defined just over x2, which is nothing but, let's say we have d data points, the probability that x2 takes the value x2I in the data set. Okay? So by definition of probability, this expression x2 equals x2I is nothing but sum out of x1 from the joint over x1 and x2 equals x2I. Okay? So now, in order to compute the likelihood, what we have to do is we have to solve a summation problem. Since we have already covered inference in this class, you can easily figure out that in some cases computing the likelihood will be very, very difficult. Okay? Because computing the likelihood is the same as solving the probability of evidence problem. And we know that computing probability of evidence is sharply hard in the worst case. So you'll have to use something like a bucket elimination algorithm in order to compute likelihood. What this slide shows is a pictorial view of the same thing that we talked about in the previous slide, and it demonstrates why parameter learning is challenging in presence of partially observed data. As we see, in the fully observed data case, our likelihood was nice and unimodal as well as decomposable, while in the partially observed data case, each point in the sum, if you remember, our sum was p of x2 equals x2I is equal to sum out of x1 from p of x1 comma x2 equals x2I. So for each value of x1, we get a unimodal distribution. Okay. However, when we combine or sum over different values of x1, we get a multimodal distribution because we are combining multiple unimodal distributions. So for instance, let's say x1 takes 5 values. For each one of those 5 values, we will get a unimodal distribution. And let's say the unimodal distributions are these. So this is for, let's say, x1 equals 1, this is x1 equals 2, this is, let's say, x1 equals 3, this is, let's say, x1 equals 4, and this is, let's say, x1 equals 5. Right? So we have 5 peaks corresponding to different values of x1. When we combine these peaks together, we get a multimodal distribution. Okay? And the optimization problem becomes harder because depending on the number of values of x1, we might have large number of peaks and valleys. Okay? So we will not get a nice closed form solution like we got in the fully observed data case. So what we are going to do is we are going to look at 2 iterative approaches for solving this problem, right? Optimizing in the presence of multimodal distributions, or I should say multimodal functions or likelihood functions. And the first approach is called the expectation maximization approach, and the second approach is called the gradient descent approach. Okay, so next class we will look at the expectation maximization approach as well as the gradient descent approach. To summarize, in today's lecture, we looked at the different learning problems we'll try to solve in this course. We saw that we have 16 learning problems, and what we'll do is we'll try to develop algorithms for each one of these problems in the next few classes. We discussed one specific learning problem in great detail, which is the simplest problem of the bunch, unfortunately. And the problem is learning the parameters of a Bayesian network given its structure as well as data using the maximum likelihood and estimation principle under the assumption that the data is fully observed. Since this problem was simple, I should say this problem was simple because we derived nice closed form expressions for the parameters. And these closed form expressions were obtained by taking derivatives of the log likelihood function with respect to the parameters and setting them to 0. We also introduced the parameter learning problem in Bayesian networks in presence of partially observed data and described why it is much harder to solve than the fully observed data case. What you should try to do for the next lecture is read the appropriate chapters that will be linked on the class webpage and brush up on gradient descent algorithms as well as the expectation maximization algorithm by reading Wikipedia article on it. So the expectation maximization algorithm, I assume, will not be covered in many of the classes that you have, or courses I should say, that you have taken before at UTD. However, if you have taken any probabilities course or statistics course or any data science course, then gradient descent algorithms must be covered in them. So please brush up on them.